Hey everyone, today we are going to be going over trusses and specifically the method of joints for solving trusses. Now today we're just going to have a simple, easy example problem to go over. We're not going to do anything too extensive because usually these problems are a little bit bigger. They have just a lot of different joints on them and you can wind up with like 12 different equations and 12 unknowns. But today we're going to stick with something nice and simple. Basically, for this problem, we have a triangle made out of beams. And each point is just connected by pin or something like that. So, up at point A, we have a force of 10 pounds acting straight in the x direction. At B, we have a roller support. And then over at C, it's pinned down. Height is 2, base is 3. Now that I look at it, it is not to scale whatsoever, but that's okay. So basically, what is the method of joints? Well, the method of joints states that the forces in and out of every point have to sum up to 0 because we're in statics here. So what we're going to find is the force that is in this member AB, the force in this member AC, the force in the member BC, and then the reaction forces at B. Anyway, and that should be it for this problem. So let's look at each point individually, which is what we have to do with these problems. So we say we're going to take point A over here, and all the forces going in and coming out of point A have to equal 0. We have our 10 pounds at point A, and then these members, these beams, turn into forces themselves. Smaller. We have B over here. We have C over here. So this is now point A. And since all of these forces have to equal up to 0, we have two equations for this free body diagram. Sum of the forces in the x equals 0, and sum of the forces in the y equals 0. Okay, and then we'll have to use a unit vector to solve this, or to break it up into its x and y components. We have a 1.5, a 2. Notice we have that because we break this 3 in half. So 1.5 is over here, 1.5 is over here. This goes down 1.5 and down 2 and over 1.5. Now we just need the hypotenuse of that, which is 2.5. And it's going to be the exact same thing for over there on that other force. So now we can split it up into its x and y components. Before we move on though, you always want to assume tension, unless you know otherwise. So what does that mean? Every point, or every force that is coming out of this point is pointing away from it. That means that it's in tension. If it's pointing towards the point, that means it's in compression. So AB, we're assuming it's tension. Now that could be wrong. And then AC, we're assuming it's in tension. That could also be wrong. Now at the end, we want to know if each of these members is in compression or tension. So what we're going to do is basically, once we solve our equations, if the number is positive, that means our assumption is correct and that our member is in tension. If our number comes out negative at the end, then that means our assumption was incorrect and our member is actually in compression. So always assume tension unless you specifically know otherwise. like this force up here, 10, we know that it's pushing that way. So of course we're not going to assume that's in tension because that would be wrong. We know that it's pushing this way. Anyway, moving on. So for the sum of the forces in the x, we have negative 10 minus, this force is going negative in that x direction, 1.5 divided by 2.5 AB plus 1.5 over 2.5 AC. Some of the forces in the y, we just have negative 2 over 2.5 AB minus 2 over 2.5 AC. And you could just solve these from this point, but I'm not going to. I'm going to just move on to our next free body diagram, which is point B over here. So for this free body diagram at point B, we have this force AB again. We're assuming tension because we don't know which way it's going yet. Force BC, also assuming tension, and then BY, I put that one pointing up because it's a roller support. This roller support can't possibly hold itself to the ground. It can just stop it from pushing farther into the ground. So that's why this is going up like that. So sum of the forces, the x for this one equals 0. We have, again, our 2, 1.5, and 2.5. 1.5 times AB divided by 2.5 plus BC is going to equal 0. Now, sum of the forces in the y equals 0. We have BY plus 2 over 2.5 AB, and that's going to equal 0. So, if we were wanting to find the reaction forces at C, we'd keep going and make another free body diagram for C over here, which would look like this. And I'm just going to assume pressure on that. Anyway, but since we don't care about the reactions at C, we're not going to do that one. We already have all of our members, and let's count up our equations and our unknowns. We have one unknown, 2, 3, 4. So 1, 2, 3, 4 unknowns, 4 equations. We can now solve this. And I would just plug this into a simultaneous equation solver at this point, and the answers we should come up with is AC equals 8.33, AB equals negative 8.33, and then let's see, BY equals 6.667, and then BC equals 5. Okay, now what did this tell us? Well, it told us that AC is indeed in tension. Our assumption was correct for this one, but AB is negative, so that means that this is in compression. It's being pushed down on this side, which makes sense when you look at it. BY is going up like we assumed it before, but it's a reaction force, so we don't specify tension or compression there. And then BC was 5, which means that was also in tension. Anyway, so that should be all that we're looking for this problem. Anyway, that is a quick video for the method of joints. Later on, we'll go over a different method of sections for this, and we'll see you next time.